It is possible to build a torpedo with winglets, so the torpedo can turn in the water and attack upwards from underneath into the hull of a ship. The terminal tracking system would be optical. It would have an acoustic tracking system at the front of the torpedo, which is the conventional tracking system that all torpedoes have to get close to the ship. There would be an optical system in the top of the torpedo. The optical tracking system would be mounted a little bit back from the bow of the torpedo, which would enable the torpedo to look upwards, see the ship, and turn over for the attack. As it turns over for the attack, the optical system would rotate outwards and forward so it can continuously see the ship for the attack. The problem with the visibility in the water is seawater absorbs sunlight. There's also other material. There can be everything from ash, silt, sand, and biomass, little plankton floating in the water, and all of that will make the water murkier and more difficult for visual observation. Most seawater in most places in the world is fairly clear. The acoustic system is necessary because you cannot see a ship from miles away from underwater. On a bright sunny day, human eyesight can see some light at a depth of about 1,000 feet in the water. The best light for transmission in water is a blue-green light. The optical system can be a low light system. It can be a laser scanning system. Therefore, there would be a blue-green laser illuminating the ship for the attack. If a torpedo is traveling at 50 knots, it is traveling at 85 feet per second. The turning radius is v squared divided by the acceleration equals the turning radius. 85 squared is about 7,200. If you have 2 g's of turning, that's 64. And the turning radius is 110 feet, about 115 feet. That would mean the torpedo could approach between 150 and 200 feet. If it can see 500 feet into the water, that would be known as the slant range to the hull. At 200 feet, the horizontal distance would be 450 feet. At 85 feet per second, that gives you 5 seconds. You need the distance to turn. When the torpedo turns, it does not turn instantaneously. It has to rotate and go into the turn. There is some time involved in that. So if you say 200 feet, initiating the turn, then the 120-foot turn, 115-foot turn, and then goes upwards into the underside of the ship, that would mean 250 feet or about 3 seconds. So the torpedo has 3 seconds to prepare itself to begin the turn in that example. There are references to the current U.S. torpedoes that claim that they weigh 3,500 pounds. They're 21 inches in diameter, something like 21 feet long. If you take that diameter, the radius is a little over 10 inches. Square it, and you get a number of about 110. Multiply it by pi to get the area, and you get a number about 340, 350 square inches. A square foot is 144 square inches. So that's a little bit under 2.5 feet, 2.4 feet. Multiplying it by the 21-foot length, and you get a number of about 50. That is just the raw dimensions, the outside dimensions of the torpedo, the cylinder that would wrap around the torpedo. The volume of the torpedo is somewhat less than that. If the 3,500 pound estimate is correct, the torpedo would weigh some 85 pounds per cubic foot. Seawater weighs 64 pounds per cubic foot. That would mean the torpedo would need some form of lift to prevent it from sinking. The torpedo would have to travel in a bow-up attitude. The front end of the torpedo would have to be elevated to produce some lift from the movement of the water to prevent the torpedo from sinking. The thrust required to travel at 50 knots is most likely over 2,000 pounds. It might require over 3,000 pounds of thrust. In order to lift the torpedo vertically, at some point, the entire weight of the torpedo plus the drag has to be accounted for in thrust. In order to have the winglets, the torpedo is going to have to be longer. It's going to be a heavier torpedo. If you're saying 4,000 pounds, there is a requirement for thrust on the order of 6,000 pounds, maybe even larger than that. The engine can be made oversized. That can make up for some of it. Then you need an additional booster. One possibility is to put a rocket motor. Now, the way you put the rocket motor on it, there aren't particularly good choices. One option is to widen out the shaft to the propeller, the impeller, and make that into a rocket motor. That gives you a very high moment of inertia, which means that starting the engine and starting the propeller is much more difficult. There's what's called the specific impulse for a rocket fuel, and that is the amount of seconds it can maintain a thrust. And for solid rocket propellants, it's a number something over 200. So if you wanted to have 4,000 pounds of thrust, even, that would mean you need 20 pounds of fuel per second. If you look at the approach into the turn and the turn upwards. The vertical distance is saying 200 feet. At 85 feet per second, that's 2.5 seconds. It's turning through an arc. You might need a good 3 seconds. That would be 60 pounds of fuel. Rocket fuel probably weighs about 100 pounds per cubic foot. It would be 60 over 100 or 0.6 cubic feet. And that is about 1,050 cubic inches. If you put it on a 3-foot length of shaft, you have to have 30 square inches of propellant. Plus you need an empty little tube down the center for the propellants to burn into and then go to the actual rocket motor nozzle. That would mean the entire package would have to be probably about 7 inches in diameter. 3.5 inches squared times pi is almost 40 inches. Subtract a good inch or so. That would be close to the dimensions necessary. And then you have a rocket motor nozzle built in to the back of the shaft with some kind of cover plate or cover cap, which would blow off before the rocket motor is started. If you have a cylinder of fuel like that, it's going to produce more thrust as it burns. The area of the propellant is proportional to the rate at which fuel burns and the rate at which thrust is produced. So if it has a small diameter at the beginning, it will have a smaller amount of thrust. As the fuel burns, it expands. There's more surface area, a higher rate of burning, and a higher rate of thrust, which is what you want. If you look at the curve, you need a little bit of thrust. It needs to increase, and then it needs to become a large value. It may not be a perfect match, but it provides a similarity to the values needed. There is also increased drag from the winglets and the turning force needed, and that also has to be compensated for by the thrust. If the engine is oversized, you would need maybe something less than 4,000 pounds for the thrust of the rocket motor. With the space requirements needed for the rocket motor on the shaft, it might be necessary to build the torpedo of a larger diameter. In order to turn the torpedo, you need to generate lift. The lift on an airfoil is typically expressed as 1/2 the mass density of the fluid times velocity squared times the area of the airfoil, and then multiplied by something called the coefficient of lift, which is a function of the efficiency of the wing and the angle of attack. At 85 feet per second, that's again 7,200, the mass density of seawater is 64 pounds per cubic foot, which is the weight of seawater. That has to be divided by gravity. That gives you a number of 2. Divide by 1/2 and you get a number of 1. So it's 7,200 pounds times the area times the coefficient of lift. An airplane can achieve a maximum coefficient of lift of over 1. And that is in a clean configuration. No flaps, no leading edge devices, just the wing itself. If the torpedo was designed to attack at 2 Gs, if it weighs 4,000 pounds, it would need 8,000 pounds of lift. If you have 4 winglets, each rotated at a 45-degree angle, each of them has 0.7 efficiency, which is the cosine of 45 degrees, the angle of the blades. So that's 2.8. If the coefficient of lift is 0.5, that would be 3,600 pounds of lift per square foot of surface area of the winglets. If it's 8,000 pounds for the 2G turning, you would need 2.2 feet. You have 0.7 efficiency times 4, that's 2.8, and each winglet would have to be about 0.8 square feet. For folding the winglets, one option is to have them folded in a left to right position underneath the torpedo. Then you'd have a skin that would peel off, a shroud that would come loose, and they would just rotate upwards. It could be about 1 by 1 square feet, which gives you about 1 square foot of area, but it's not as efficient as a longer, thinner winglet in producing lift. The other option is to put them in pockets going from front to back and have them rotate upwards, kind of like a switchblade knife. If they're 2 feet long and 1/2 foot, 6 inches, from front to back cord length, that would give you a number of 1. The blades are curved, so the area is going to be smaller than that. So the winglet extended outside of the torpedo could be a little over 2 feet by 6 inches. If you use those pockets, the material has to resist the forces of seawater. At 1,200 feet, the pressure is about 76,000 pounds per square foot, or about 550 pounds per square inch. And you would need the material to be heavy enough to resist that, strong enough to resist that. In order for the torpedo to rotate quickly and go into the attack, there has to be enough turning authority at the back end of the torpedo, which means you might have to have additional winglets fitted to give you that level of rapid turning. Overall, you have a torpedo that's larger, heavier, more expensive, but which would be more effective at attacking ships.